Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel where we talk about everything I want to, science and math. And what we're doing today is this chemistry class, and we are learning about reaction rates and equilibrium. So some reactions go faster than others, and you know this because one of the reasons why you decided to take chemistry is you wanted something to explode. You wanted to see a fast reaction, right? So we don't do many explosions anymore. In fact, they have, the public school where I teach, there's rules. The Board of Education has rules that you're not, like on the periodic table, I'll show you this. If you put this column in water, the further you go down, the more it explodes. So when I first started teaching, I would always order sodium and put it in water, and it would, on a good day, it would fizzle around and catch on fire. One day it went kaboom and caught the ceiling of my lab on fire. I think it was contaminated and had maybe some potassium or something in it. There was no reason for it to kaboom. But at my new school that I teach out in a different county, they don't even let us order these things. They don't let us do anything with that first column. So even the one that would be less reactive, like the lithium, they don't let us do it. So anyway, reactions can happen at different rates, right? They can be faster or slower. Concrete takes years to harden, and that's part of that's a chemical reaction that's very, very slow. And also there are things that can affect reactions. So like your book talks about, that it could have taken millions of years to make coal, but there could have been other things that could have that could have caused that reaction. There could have been other factors that we're going to talk about that could have sped it up. So unless we were there, it's hard to know. We have to always be careful about speculating about where we weren't there in science. We want to see things. We want to know things we can observe and that we can repeat. Not just, but of course we do want to speculate about the past, but we can't be set in stone because we can't run repeatable experiments on it. Okay, does that make sense? All right, so reaction rates and collision theory. So we can speed up a reaction if we can get the particles to collide better. If they can collide more often, if they can collide harder, if you have more of them colliding, we can speed up a reaction. Now, with reactions, let me get a little piece of paper here and show you. We can diagram reactions. Let me see. Whoop, there's a little. You can ignore the little algebra across the top. We're going to look at the bottom part here. This is a typical sort of reaction diagram. You have your products, you have your reactants, and often there is a hump of energy you have to get over to get them to react. For example, I have a candle right here that can react with the oxygen in this room and burn. Am I worried that the candle is going to start burning all by itself in the middle of the night while I'm asleep and catch something on fire? No, because it has to have that activation energy. It has to have that extra energy to get over the hump to get it started. And then that's me lighting the candle. But once it's lit, it will continue on its own. I don't have to keep holding the lighter on the candle. It will be able to do that all by itself. So there are things that can speed up a reaction. One is to give it the, there are ways that you can like add a catalyst, which will lower that activation energy. Another thing that you can do to make something react faster is usually you can heat it up. If you heat it up, the particles move faster, they're more likely to react. Another thing you can do is have a greater concentration. The more particles that are there, the more likely they're going to run into each other, collision theory, the more likely they're going to react. Another thing is particle size. Now this one is a little hard, so to wrap your head around it, the smaller a particle is, the greater surface area it has per volume. Let me say that again. The smaller a particle is, the greater surface area it has in relationship to its volume. So if you break up a particle into smaller pieces, it's got a bigger ratio of surface area, the more likely it's going to react. And you know this, it's easier to catch sawdust on fire than a big old Yule log. It's very hard to get a log going, but little bits of straw, little bits of like if you were going to catch on fire the shavings from a pencil sharpener, that'd be easy to do because of the small particle size. I live in the southeastern United States, and here we're not as familiar with this. We have very humid air here. It is always moist, year-round, extremely humid. But out west, it's drier, and they grow grains, corn, and things like that. And where they take the grains into these grain silos and to sell them and things like that, they have to be really, really careful about the corn becoming dust, because if so, it can combust and cause explosions, fire, death, destruction. Hold on, I got a low battery warning. Let me turn that off. So it means I gotta talk fast. But you never worry about your area of corn on the cob exploding and blowing your head off. But out west, they have to be very careful about grain silo fires, because the smaller particles that dust becomes, the more explosive and volatile it is. So how I kind of remember it is, which dog shivers? The Chihuahua or the Saint Bernard? It's the Chihuahua. It's because he's so small, he has a greater surface area, he loses his heat to the environment, he shivers. Big old fat Great Dane, Saint Bernard, they don't shiver. They have very low surface area per volume. All right, so particle size, the smaller they are. And there's something I want to buy. I'd forgotten that. I want to buy the fire syringe. I'm going to make a little note about that. Fire syringe. You can take a cotton ball and put it under pressure with more air, and it'll catch on fire. How cool is that? So that'd be a fun thing to do. Okay, so catalyst, I already told you, sometimes you can add a chemical that doesn't actually take place in the reaction, but it can lower that activation energy, or it can cause chemicals to get together to react. In your body, you have something called enzymes you should have learned about in biology. And enzymes are proteins that'll go get one thing and another thing and get them together so they react. They're like matchmakers. The matchmaker is not part of the wedding, but the matchmaker can introduce the bride and groom so that they can get married. Does that make sense? So enzymes are important catalysts in your body. Reversible reactions. Okay, a lot of reactions, you put the stuff in, it goes, it makes a reaction. But there are some things that it will make a product, but then you can reverse it and you can get the reactants back again. You're used to this because you know about rechargeable batteries. Rechargeable batteries start off with one chemical, it reacts, you run electricity through it the other way, and you can get it back to the original products a lot of times until your batteries are no good anymore. And you can recharge your phone, you can recharge your video game stuff by having a reversible reaction. Now, there are certain things that could cause, when a reaction is reversible, where it can go back and forth, it reaches a point where if nothing's pushing on it, like the electricity going through it backwards, it reaches a point where the products and the reactant concentrations are staying the same, and that's called equilibrium. That equilibrium can be shifted more toward products or reactions. It's called Le Chatelier's principle, and I know I'm saying that wrong because it's French and they don't say those letters, so you'll have to Google to see how to really say his name, but it's spelled Le Chatelier's, and I know that's not how it's said. But anyway, you can like sometimes add heat and it'll make it go more toward products. You can add products and it will go back toward reactants. So you can shift equilibrium. Now that is an idea we do more in Chem 2 or AP Chem, but I always like to introduce it in Chem 1. So be sure to read through that part in your book about how you can. Another thing that can cause reactions to go better is pressure, especially like if it's gases, where it is getting together. Now, energy, chemistry is all about energy, and we want to talk about a spontaneous reaction is one where you just put it together and it goes, and they have a good. And the non-spontaneous reactions, you might have to heat it up or something like that. Now, entropy. Entropy is an idea like gravity. It is something that's a law. Remember, laws beat theories. And it is the law of entropy. It's also called the second law of thermodynamics. And what it says is that in nature, things go from order to disorder unless acted upon by an outside force. In your book, it has a picture of a messy room. That room is messy. It is not going to clean itself. And the only way for it to get clean is for you to get in there and be the outside force that acts on it and put it to order. Things go from order to disorder naturally. Another example of this is we live in the Atlanta area. We would go to Six Flags Over Georgia. And when the Six Flags Over Georgia was new, there's a ride there called the Dahlonega Mine Train. And when I was a kid, they had the Dahlonega, they had out there, Imagineered, they had a covered wagon. Well, over the years, the cover got torn off, then the little things that go over rotted, then the wheels rotted off, then the wagon rotted and rusted, and now it's just some pieces of metal out there. It is so pitiful. Disney would never have done this, Six Flags. But Six Flags just let that thing rot out there over from the time I was a kid to now, and you know that's been a few decades. But it shows entropy that left unattended, without somebody taking care of that covered wagon, it went from order, a nice covered wagon, to disorder, rust, and torn apart. So this is a law. It beats theories. Remember that. So in our reactions, the same thing happens. If I had a bottle of perfume and I open it up, those perfume molecules, those scent molecules are going to come out of that bottle and spread throughout the room. It's going to go from order, all being in the bottle, to disorder. And there is no getting them back in the bottle unless acted upon by some outside system that I can't even imagine how you're going to get the perfume back in the bottle. So, also there is something called equilibrium constants. There's a way to calculate what the concentrations of these reactants and products will be in a reaction, and it is a number called a equilibrium constant. They show you in the book how to do these problems. These would definitely be in an honors chemistry class or AP or Chem 2. So take a look at them. They're not hard, but take a look at them, and you're just plugging it into this formula, the equilibrium constant. The math's not hard. So if you want to take a look at that, you can. If you want to skip it, you have my permission. You may skip it also. Same thing with entropy calculations. You'll do more of that in physics class. We talk about entropy all in physics too. And free energy. All of that is more advanced, and rate laws. Take a look at those problems. If you want to do them, go for it. We're going to be doing a lab about the effect of temperature on reaction rates. It's fun. You're going to heat up water and throw Alka-Seltzer in and see what happens. Also, reaction mechanisms. Reactions can take a place in one step, or it can take a place in many steps. And a lot of times you would have to figure out the steps of how a reaction happened. And that's what you do a lot in college chemistry. My older son, Nathan, was a chemistry major, and now he's in a PhD program, and he spends a lot of time figuring out reaction mechanisms, and more power to him. That's not what I think of as the fun part of chemistry, but he loves it. He thinks it's like a slidey puzzle, and it's very fun to figure it out. All right, come back next time and we'll talk about something that's maybe a little bit more familiar: acids, bases, neutralization reactions. All right, like, share, subscribe, and remember, science is great.